Hi friends, welcome to our YouTube channel. In this video, we are going to show you how to design Disturbance Observer for Twin Rotor Aerodynamic System using H-infinity approach. You can design Disturbance Observer using H-infinity approach for your own system in Matlab after watching this video. So, we will complete this in the following steps. Step 1. Find a system. You have to choose a system. This is Twin Rotor Aerodynamic System. It is generally used in the research labs for testing the effectiveness and performance of controllers that are designed for helicopters and vertical takeoff rotor crafts. This system consists of two motors called main rotor and tail rotor. These rotors are mounted on a beam. This is the beam, and these motors are mounted on this beam. This motor is called main rotor and this is called tail rotor. The beam is pivoted on a base. This beam is pivoted on this base, and this beam can rotate and move freely. This beam can move freely in both horizontal and vertical direction. This is horizontal direction and vertical direction. The vertical displacement of this beam, the vertical displacement and motion of this beam is dependent on the motion of the main rotor. Whereas the horizontal displacement or motion of this beam is controlled by is dependent on the motion of the motion and the speed of the tail rotor. So our task here is to control the pitch angle, vertical motion of the beam, and yaw angle, horizontal motion of the beam, horizontal displacement of the beam, and the presence of disturbances. Second step is to obtain the mathematical model of our system. So, this is the mathematical model of Twin Rotor Aerodynamic System. It consists of 4 equations. These are non-linear equations that describes the mathematical model of Twin Rotor Aerodynamic System. This is the first equation, second equation, third equation, and fourth equation. Derivation of these equations can be found in the attached paper. So if you need how to derive these equations, you can check the attached paper. Link is given in the description. This non-linear model, we have implemented in Matlab Simulink. So these four nonlinear equations are implemented here. So this is the nonlinear model of twin rotor aerodynamic system. It has two inputs and two outputs. One output is called pitch angle and second output is called yaw angle. The parameters given here like K1, T11, T10, B1 psi, all these parameters are defined here in the M file. This K1 has value 1.11, T11 has value 1.1. So all these are non-linear parameters of twin rotor aerodynamic system. The next step is to linearize the model. This model that we have obtained in the Simulink, we have designed, we have implemented in the Simulink. So we need to linearize this system. We have to obtain ABCD matrices, state space model from this nonlinear model. So here is the linear model of twin rotor aerodynamic system. This is the A matrix, B, C and D. So you can check here it has two outputs and two inputs from B and C matrices. Watch our previous video on how to linearize a nonlinear model in Matlab. We have already made a video on this. When we are given a nonlinear Simulink model of any system, we can linearize it using Matlab Simulink. So we have already made a video on this. You can check this in our channel. Now, from the state space model, we obtain the transfer function matrix as G of S. So these are the four transfer functions. As we have two inputs and two outputs, this is the transfer function from input 1 to output 1. This is the transfer function from input 2 to the output 1. This is transfer function from input 1 to output 2. And this is the transfer function from input 2 to output 2. Now we can check here, we can see here that there is interaction between input 1 and output 1, input 2 and output 2. There is no interaction between input 2 and output 1, but there is interaction, there is a transfer function from input 1 to output number 2. This is called cross coupling effect, which is undesirable. So to minimize this cross coupling effect, we will need to design a decoupler for our system. Decoupler for our system. So visit the attached paper and the description of the video to see how to design decoupler. We will not waste our time on decoupler. Next step is, as we have obtained the linearized model, ABCD matrices, and we have obtained the decoupled transfer function of our system. So Now the next step is to design controllers for our system to meet the performance specification. Performance specification like settling time, rise time, and steady state error. These are called performance specification. For these we will first make controller. So here we will make LQG controller, linear quadratic Gaussian controller for our system. As we have decoupled our system in two subsystems, one is called the main router and second is called the tail router subsystem. So first we will design LQG controller for the main router. So video on how to design LQG controller in Matlab is already uploaded. So we have uploaded how to design LQG controller. Full explanation is given in the video. You can check there. This is the code for linear quadratic Gaussian controller for main router or twin rotor aerodynamic system. GM represents the transfer function of the main router. So we will run it, this code. And where to obtain the LQG controller parameter for our system, subsystem, main router. So we have obtained successfully the controller step response of main router using LQG controller. Design LQG controller for the tail router. Now as we have, this is for the main router, now this is for the tail router subsystem. You can see here this is the overshoot for, but this overshoot is with the linear model. With a non-linear model you will see this, that this overshoot is minimized. Now in this step we will design disturbance observer for the main router. So this is the code for disturbance observer design for the main router of the twin rotor aerodynamic system. This approach is the same as we have discussed in our previous video, design of H infinity controller. So here we obtained gamma value 0.7109. Now this is the disturbance observer for tail router. Now this is Twin Rotor Aerodynamic System non-linear model, and this is, now check here, this is our Simulink model of twin rotor. Simulation of the whole code is there. This is the non-linear model of trace. This is the decoupler we have designed. This is the LQG controller. LQG controller. These things are from LQG controller. This is the main rotor LQG controller, and this is for tail rotor. This is for tail rotor. Now this, here you can see, this is the disturbance observer of the main rotor. AK main, BK main, CK main, DK main. Is we have defined these here. And this is disturbance observer for the tail rotor. AK tail, BK tail, CK tail, DK tail. So let's simulate without disturbance observer, then with disturbance observer. Now this is the response of our system with non-linear model of twin rotor aerodynamic system. This is the main rotor and this is the tail rotor. This is response without disturbance observer. Now we can check with disturbance observer. Here smooth response with disturbance observer, because some of the uncertainties are removed. If we add output disturbance here, so let's check first without using. Check this. This is without disturbance observer. Now if we connect disturbance observer, then you can check this disturbance is fast removed. Disturbance observer using H-infinity approach has the same procedure as H-infinity controller design, except that you have to change the generalized plant configuration. This is the generalized plant configuration for disturbance observer design. Here you have to include the controller C of S in the generalized plant matrix P. And the other thing you will change here is you have to minimize the H-infinity norm from the noise and external disturbances to the disturbance estimation error.